Oh, it's very dark. We got light up. Okay, so we are doing chapter 5 notes today. We're starting chapter 5. We are still doing trig, so you'll still see a lot of sine, cosine, tangent, but we're gonna actually be doing something called simplifying and verifying identities. So that's what your blank sheet of paper is for trig identities, trig formulas that we're gonna keep using throughout this unit. So we're gonna keep adding onto this sheet. Eventually it'll look something like this. See how like I've got a ton of little formulas on here? Instead of me just giving you this to start, we're gonna build it ourselves, okay? So we're gonna build it as we go. But before we start that, I think we can actually do the first couple problems ourselves. So the first one, it says no calculator, and it says find sine and cosine if tangent of theta is 3/4, and then sine, and it looks like it got cut off. Let's say that that says sine is greater than 0. This is like those triangle problems we saw a lot of back in chapter 4, right? If tangent is 3/4, what quadrants could it be in? First, and which one? Quadrant 1 and quadrant 3. Good, quadrant 3, good. And then if sine is greater than 0, where could sine be? Or where could the graph be, I guess? 1 and 2. Now, what place where they overlap is in quadrant 1. So we're going to go draw our triangle in quadrant 1. And the tangent is 3/4. So we can label our which two sides as 3 and 4. Very good, opposite and adjacent. So I'm going to jump over here and I'm going to draw my little coordinate plane. Draw my triangle. Put my angle in by the origin, and I'm going to label my opposite as 3 and my adjacent as 4. Hey, now that I've done that, could you find the hypotenuse? Yep, Pythagorean theorem. We've done this kind of over and over. You're probably like, yes, we could do this problem in our sleep. That's how confident we should feel in it. 9 plus 16 equals x squared, and that's 25. And so x equals 5. Once I've done that triangle, now I'm ready to just figure out what cosine and what sine are. Can we do that just based on the picture that we have now? Absolutely. So over to the side, I'll write good, sine of theta equals 3/5 and cosine of theta equals 4/5. All right, everybody okay with that? Okay, the next problem is super similar, and I think you can do that mostly on your own. The one thing I do want to add is it looks like it got cut off again. It should be tangent of theta is less than 0. So take a second, decide what quadrant you're in, decide what your shape looks like, label your triangle, find the missing side, etc., etc. And I'll show my work up here, but I'll be quiet so not to disturb you. All right, and I've got my work up on the board when you need it. There. I did not do Pythagorean theorem out because it was the exact same numbers as the last problem. Are you guys okay with that? So if you did Pythagorean theorem out, that's okay. You should have gotten 3. But since I'm in quadrant 4, make sure it's negative. All right, we doing okay? All right, let's start building our identity sheet. So go ahead and put your notes off to the side for a second. Get your lined paper. The first few identities I'm going to teach you, I think you already know. I think we've already kind of reviewed over. And so I am going to jump down. I just added a page in here and I labeled the sheet trig identities and formulas. And I actually started by making like a little kind of chart or graph for 8 functions altogether. 2 columns of 4 rows, because they're going to go together like that. So if you like yours kind of set up similarly, go ahead and make sure that yours looks something like that. These first few are normal. They are ones that you should be familiar with. I guess if we wanted to have a name for them, we could call them like reciprocal. So I can use it. There are reciprocal trig identities. And when I say reciprocal, what do you think in your head? What does reciprocal mean? So we're going to flip them. So I'm going to say sine. Do you remember which trig function goes with sine? CSC, very good, Chase, CSC, so cosecant. Sine is the same thing as 1 over cosecant. Which means that next to it, which is why I put them next to each other, I'm going to write CSC. And what's that going to be equal to? 1 over sine, good. So these are the reciprocal functions of each other. So each one is equal to 1 over its like partner. Okay. On the next slide, I'll write cosine. Cosine is equal to 1 over what? SEC, secant. And so then secant is equal to, thank you, 1 over cosine. And then the last one is going to be tan. So tan of theta is equal to 1 over cotangent, good. And then vice versa, cotangent is equal to 1 over tan. Now you might be like, cool, Miss White, we got it. I know what all 6 of those are. We've seen all of those. We've had them match up before. Why is there an extra line? Okay. One trick I'm going to ask you to do a lot when we're doing our simplifying and our verifying, which we haven't done yet. So you're probably like, I have no idea what's happening. That's okay. One thing I'm going to ask you often is how do we put everything in terms of just sine and cosine? So notice that sine and cosine are written as they are normally. I can rewrite cosecant as 1 over sine, and secant is 1 over cosine, but tan and cotan are not written as sine and cosine. I'm going to argue we can do that. So let's figure that out, okay? We know tangent. What is that in terms of x's and y's? Tangent is what? Y over x, okay? And you don't necessarily have to write that down, but I write that down simply to remind myself which trig function goes with y. Sine, and which trig function goes with x? Cosine. So tangent is the same thing as sine over cosine. So if I say rewrite everything in terms of sine and cosine and we have a tangent, we're going to take that tangent out and we're going to replace it with sine over cosine. Okay. Similarly, cotangent. Well, you know 2 things. One, you can just do the reciprocal from tangent, or I can again put it in terms of x and y. Cotangent is x over y. So then when I rewrite that, I get cosine over sine. It's also like in tangent where it's sine over cosine, you can just do the reciprocal, put cosine on top. Okay. We're going to pause with just those. We're going to do a couple things. So we're practicing just using these reciprocal ones, and then I'm going to add some more identities here. Is everybody okay with what I've said so far? Everyone's cool on how I got that, how I know all of this. Okay, these are now our reference tools. So you don't necessarily have to like have them at the top of your brain right now, but you need to go look at the sheet in order to know it, okay? So we're gonna jump back over, and number 2 has a bunch of simplified problems, okay? And I think we can do all of A, and I think we can start D with just these identities, okay? So let's go to letter A. Remember a second ago, I said something I'm gonna ask you often to do is put things in terms of sine and cosine. That's how we're gonna start this one. Can we rewrite tan x times cosine x in terms of only sine and cosine? Yeah, what can we write tan as? Good, sine over cosine. And you can make it x, you can make it theta, it doesn't matter to me. And then the cosine x is already written in terms of sine and cosine, so I'm just gonna leave it as cos x. Now, what might help me is, can you make cos x a fraction? It would be cos x over 1. They cancel. Good, so I'm gonna cancel these cosines out, and what am I left with? Sine. Good, that's it. Simplifying means that we're gonna get it down to one trig function. Every so often, it might be like sine plus 1 instead of just sine, but generally it's one trig function. So that was it. You did your first simplifying problem. That wasn't too bad, was it? Okay, let's go to D. We can't finish D, but we can start D right now. We'll finish it in a minute. So on D, I'm gonna start. I do want to put things in terms of sine and cosine, but let's start by distributing that sine to everything. So I want to get rid of that parentheses. I'm trying to break it down. So we're going to multiply sine by everything in here. So I've got sine of x times tangent x plus sine of x times cotangent x. So first thing I did is I distributed that sine to everything and got rid of the parentheses. That's good. Now I want to put things in terms of sine and cosine. Can we rewrite tan and cotan in terms of sine and cosine? Okay, let's do it. I still have that sine x in front, but tangent is now sine over cosine. And cotangent is now cosine over sine. Okay. See how nice and clear I wrote it out? You can also make those sine x's over 1, so you can see any canceling or any combining we can do. In the first part, can I do any canceling here? Is there anything that crosses out? No, so we're just gonna combine it. We can multiply sine times sine. What's sine times sine? Sine squared, good. All over cosine. And then what about my second part? Can I cancel anything out there? Those sines cancel out, right? So we're just gonna be left with cosine. And again, we'll think of that as cosine over 1. Yeah. You don't put your square behind your x because we're squaring the trig function. We're not squaring the x. That's a good question. I asked, can I put my square behind the x? And I said, no, put it behind the trig function. Okay, as of now, we can't simplify that anymore. Okay, let me go teach you a couple other identities so that we can simplify that as we go. Okay, so go ahead. We're going to put a pause on these problems. We'll come back and do more, but I've got 9 more identities to teach you. This time I made it like a big 3x3 box, so I have 3 rows and 3 columns. And these, if you want to label for them, these are called my Pythagorean identities. Pythagorean identities. Okay, I'm gonna zoom out a little bit just so I can kind of draw the proof of this. You don't need to draw the proof. I just want you to kind of know that I didn't come up with this. This isn't BS that I just like came up with off the top of my head. There's a reason that we're allowed to do this, okay? The first Pythagorean identity that everything else is going to come from is going to be this. This I do want you to write. Sine squared x plus cosine squared x equals 1. Now you could have written theta or x, it doesn't matter. Let me just write that a little bit bigger. Sine squared x plus cos squared x equals 1. You can use theta, you can use x, you can use alpha, I don't care what you use, but those are just the variables. Now, how I got that. I told you it's a Pythagorean identity, which means it comes from the Pythagorean theorem, right? Again, you don't have to draw this, but if this is interesting to you, you can, okay? We're gonna take our unit, basically a unit circle, okay? So I've got my circle over here. And I've got a point over here on my circle. We'll put it here. It's not 30, 45, or 60, okay? We'll call this point, I don't know, it can be any x, y, I don't care. My x is my horizontal distance, right? That's that left and right movement. And my y is my vertical movement. On a unit circle, do you remember what my hypotenuse is on every single one of those triangles? It's the radius. So yeah, so how far are we around the circle? Like if I come up here, what was that? If I come over here, what was that? What's the distance from the middle to the outside of the circle? In a unit circle. Remember I told you the word unit meant one. So we are 1 unit away at all times. That's why when we do 90, we're up at 0, 1, because it's a radius of 1 the whole time. Okay. Now, if I were to do Pythagorean theorem here, we would just do y squared plus x squared equals 1, right? Now, remind me when we do the unit circle, y is the same thing as which trig function? Sine. So I can replace y with sine squared. X is the same thing as which trig function? Cosine. So I can replace x with cosine squared, and then 1 squared is just 1. So that's how I derived this formula. Kind of see where it's coming from? Now, am I ever going to ask you to replicate this? Never. But I want to just show you that there's a reason on why we know this. It just didn't come out of thin air. I'm not just be like, hey, know this thing. There's a reason it comes from. And that's why these are Pythagorean identities. Okay. Now, the 2 boxes underneath it is just going to be the same formula, but we're just going to solve it for each different part. Okay, so right now we have 1 by itself. Okay, let's get sine squared by itself. What would I have to do to get sine squared by itself? Minus that cosine. So that means you don't have to write this on this part, but I would essentially minus cos from both sides. And that means underneath it, my new formula would be sine squared x equals what? Good, 1 minus cosine squared. So we write them all in all the different ways just so you can identify them. You don't necessarily have to do this, but I think it's nice. We'll do it one more time. Now we want cosine squared by itself. So we would have to have subtracted that sine squared from both sides, right? And so my last box is going to be cosine squared of x equals what? 1 minus sine squared. Good. Good. Make sure all of your sines and cosines have squares with them right now. That would be silly to lose that square. Okay. So I gave you my original function and we wrote all the ways that we could like get each part by itself. We've got 1 by itself, we've got sine squared by itself, we've got cosine squared by itself. Okay, now we're gonna alter this first one, okay? And again, don't feel like you have to write this down, but I'm gonna show you how I'm gonna get to the next step. What if we divided by sine squared for everything? If I divide everything by the same thing, then mathematically my equation is still true, okay? What would I get when I do sine squared divided by sine squared? Well, sine squared divided by sine squared is just 1. What's cosine over sine the same thing as? Cotangent. So that's going to be cotangent squared x. And then what's 1 over sine the same thing as? Look up on your notes. Oh, let's see. 1 over sine cosecant, so that's gonna be cosecant squared x. So we took the original function I showed you that I proved from the Pythagorean theorem, and we just divided everything by sine squared, and now we've got a whole new set of trig functions that are true, okay? So now I've got 1 equals cotangent squared, or 1 plus cotangent squared equals cosecant squared. Okay, just like we did before, let's solve for each of them. So let's say we want 1 by itself here. 1 is gonna equal what? 1 equals. Good, cosecant squared minus cotangent squared, good. And again, if it helps you, all I did was I minus cotangent squared from both sides. Okay. Now, if I want cotangent by itself and I want to move the 1, now we're going to minus 1 from both sides, and I'm going to get what? Good, cotangent squared equals cosecant squared minus 1. Good. All right, everyone hanging in there so far? Okay, the last one, again, we're gonna go back to the very beginning. Remember, I just divided everything on the original function by sine squared? What do you think I'm gonna divide everything by now? Cosine squared. And again, you don't have to write that down. I'm just proving to you how I'm getting to each of these. What's sine squared divided by cosine squared? Tangent squared, very good. What's cosine squared divided by cosine squared? 1, good. And then what's 1 divided by cosine squared? Secant squared. There she is. Okay. All right, now we're gonna take each of these and solve to get the different parts all by itself. Thank you. Yes, grab one of each of those and then get out a blank piece of paper. So if I wanted tangent squared by itself, tangent squared is gonna be equal to secant squared minus 1. And then if I wanted 1 by itself, what would I have? 1 equals secant squared minus tangent squared. All right, now you still are not going to be super comfortable with all of these, but these are more tools now that we have that we can use that we're going to use to substitute or to simplify. Okay, so go ahead and have this next to your notes. We're going to jump back to our notes and we're going to use this kind of as a key. Okay, what I would do right now is just take a picture of that and then write that down later. And then you're going to be a little lost for a second, but I promise you'll either catch up or I'll catch you up later. So we're gonna go back to our notes, and we had already done number 1 because there were no squares in there. Notice all the ones that I didn't touch and where I stopped on letter D, we had squares. We had square, 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 square. That's how I knew that you weren't ready because we hadn't done any of our square Pythagorean identities. So that's why I stopped and I didn't do those yet. Let's jump in on letter B first, okay? I told you one trick was to find everything in terms of sine and cosine. Another trick is to just go to your identity sheet. Do you see any of these on your identity sheet? Do you see 1 plus tan squared anywhere on your identity sheet? What's that the same thing as? Secant squared. So 1 plus tan squared is the same thing as secant squared. Now, I know cosecant squared is also on there as 1 plus cotangent squared. I don't want to expand that out. I want to keep it down as 1. So we're going to keep cosecant squared the same. because now I'm gonna make you put it in terms of sine and cosine. What is secant squared as sine or cosine? Secant squared is what? 1 over cosine squared. And what's cosecant the same thing as? One over sine, 1 over y, which would be 1 over sine. So 1 over sine squared. Now I've got a big ugly fraction. How do I simplify that? Multiply by the reciprocal. So I've got 1 over cosine squared x times, and then I reciprocal to be sine squared over 1. That's helpful, but is there any crossing out I can do? No. So then that just becomes sine squared x over cosine squared x. But wait, is that somewhere on your identity sheet? Tan, good. So that's going to be tan squared x. Yeah. Cancel because there's a plus sign between them. Yeah, so we'll go back and finish that one in a second. All right, so you see how that very beginning, we just had to use that puzzle piece that we knew and replace it with secant squared, and then we could simplify it using what we're used to using. So tan squared is one trig function. We are done. We are simple. Okay. All right, can we jump to letter C? Does letter C look like something on your identity sheet? It kind of looks like that first one, right? Ours just says sine of x plus, or sine squared of x plus cosine squared of x. However, if you think of these as just any angle, you can have any angle there. The angle could be negative x, it could be 30, it could be like 720. It doesn't matter what it is, as long as they're the same, you can have sine squared of that plus cosine squared of that equals what, Chase? 1. That's it. So that answer is just 1. Okay. Let's look at letter E. I've got secant squared of v minus tan squared v. I've got cosine squared x plus sine squared x. Anywhere on your paper, do we have anything about cosine squared minus tan squared? What does that equal? 1. What about cosine squared plus sine squared? 1. What's 1 divided by 1? 1. That was fun. It would feel a lot harder if we didn't have our identities, but because we have our identities, you'll go to your paper and that is actually equal to 1 on your identity sheet. This is actually equal to 1 on your identity sheet. That's why we can replace them. That's why we can substitute. Okay, we do need to finish letter D though. We still have a little bit of work. Okay, I am not down to 1 trig function here. Sophia did just ask a really nice question. She goes, why can't my cosines cancel? And I said, because there's a plus sign between them. They only cancel when we had that multiplication, but the plus sign does not mean that they can cancel. However, the plus sign means that we now have 2 fractions that we want to combine together. What do we need to do in order to add these 2 fractions together? Good, cosine x on the bottom. We need like denominator. So we're going to put cos x on the bottom. And so that means now I can add them together. On top, I'm going to have sine squared x, and then cosine times cosine is cosine squared x. And then the bottom, because they have the same denominator, is just going to be cosine. Now, wait a second. What's sine squared x plus cosine squared x? 1. So I can replace all of that numerator with just 1, and I get 1 over cosine. And let's go one more step. What is 1 over cosine? Secant. Wow, you guys are on it. Oop, I didn't mean that. Okay, you feeling all right? Now, at this point, I don't need you to feel like you can do it on your own, but do you understand why I've done everything I've done? Okay, go ahead and flip your paper over. We're gonna do letter F, and then we've got a couple new different types of problems, and then we'll be done for today. We are gonna spend more time tomorrow reviewing. I've got like more of those kind of practice problems that we were just doing for you to work on your own, for me to kind of see where you're at on your own on these. Okay. Sorry, Kate. All right, go ahead, flip your paper over. We will never do letter G, I just don't want to. We will do letter F though. So first thing I want to think about for letter F. One of the tricks I told you was go look and see if the whole like 1 plus secant squared is on your identity sheet. You're welcome to do that, but that's not all one fraction yet. Somebody in my last class was like, oh, well, we could get like denominators. I'm going to argue not yet. What's the other trick that I keep going back to? Get everything in terms of sine and cosine. So we want to get everything on here in terms of sine and cosine. So this first guy, 1 over sine squared x, that's actually good where it's at. So I'm going to leave that as 1 over sine squared x. Now secant squared and tan squared, though, we can make those in terms of sine and cosine. Secant's the same thing as 1 over cosine squared. And then tan is the same thing as sine squared over cosine squared. At this point, a lot of people are like, well, tangent's also 1 over cotangent. Well, I didn't say get things in terms of cotangent. I said get things in terms of sine and cosine. And so that's why we wrote tan is equal to sine over cosine, so I can use that. Good, we're going to multiply by that reciprocal. So I still have my 1 over sine x, sine squared x. That's just kind of getting carried along with me. And then my fraction now is going to be 1 over cosine squared times, and I flip the denominator, cosine squared over sine squared. Cancel those cosines. So I've got 1 over sine squared x plus 1 over sine squared x. Huh, that's not bad. Normally I'd say let's get like denominators, but we already have them, right? What's 1 over sine squared x plus 1 over sine squared x? 2 over sine squared x. All right, this last step isn't hard, but sometimes it messes with our minds a little bit. On our identity sheet, we don't have 2 over anything, but we have sine in the denominator. What do we call it when it's sine in the denominator? Cosecant. So I can make that sign go out of the denominator by making it cosecant squared, and that 2 is just that coefficient out front. 2 is just that coefficient out front. So 2 cosecant squared x is my answer. All right, we doing okay so far? Okay. Let's go ahead and jump down. We're going to do all of number 3, maybe some of number 4. This one's a little bit different. And I'm going to argue you don't need your calculator here either. Okay, this is going to take us back to unit circle stuff. So remember when I made you memorize the unit circle, I was like, we're going to use it for a long time. That's why it was on your last test. So it still should be pretty fresh in our heads right now. Okay, these say solve, which means we want to get x by itself. We're not going to be able to get x all the way by itself, but if we can split it into just trig functions, that would make it easy. First thing I look at when I'm here is there something I can take out of both of those terms? I've got 2 cosine x sine x minus cos x. What can I take out of both of those? Cos x, good. So we'll take that cos x out. Bless you. Bless you. Bless you. Bless you. Bless you. All right, 2 cos x sine x, when you take the cos out, just becomes 2 sine x. And then negative cos x, when you take that cos out, just becomes -1. Okay, now that we're here though, we're able to set each of our factors equal to 0. I have, if you remember one of the fundamental theorems with algebra is like when it's factored out like this, you set the first thing equal to 0, and then we set the second thing equal to 0 as well. So that's what we're gonna do. Each of these are gonna be two different equations. So we'll do cosine of x equals 0. This is just like the inverses that we've been doing the last couple of days. I asked myself, what angle has a cosine of 0? What angle has a cosine of 0? 90. And then this says that we need to go all the way from 0 to 360. Is there anywhere else on the unit circle that has a cosine of 0? 270. 270. Good. So remember, cosine is your x value. All right, yeah, JT.
Negative 270 or is that?
Oh, it's just like a colon, sorry. I'll get rid of it, I'll just make it a comma. Positive 270, good question. All right, now we're gonna do the same thing, but we're gonna do the inside function. We're gonna do 2 sine x minus 1 equals 0. Now we gotta do a little solving to get that sine x all by itself, right? We're gonna add that 1 to both sides. We're gonna divide by 2 on both sides. So I get it all the way down to sine x equals 1/2. So again, we had to get our trig function all alone. So now I ask myself, what has a sine of 1/2? Sine is y 30 degrees. Where else do we have a positive sign? Quadrant 2. What's my 30-degree angle in quadrant 2? 150. Good. So all 4 of those answers work. If I plugged in 90, 270, 3, or 30, and 150, I would get 0. That would all work out. Okay. A little bit tricky, but not too bad, right? Let's go do the next one. This one says, square root 2 tan cosine x minus tan x. What can I take out of both of those terms? Tan x, good. So we'll take that tan x out. And we'll be left with root 2 cos x minus 1 equals 0. Now I'm gonna, again, just like we did before, we're gonna set each of those pieces equal to 0. We'll set the tan x equal to 0, and then we'll set that root 2 cos x minus 1 equal to 0. So when I ask myself tan x equals 0, I'm thinking, okay, y over x equals 0. 0. And then what's the other angle that has a y of 0? 180. I'm not going to notice that the range up here has a parentheses with 360, so we're going all the way up to it, but we don't have to include it. Okay, same idea. Now we're going to set the inside equal to 0. So I've got root 2 cosine of x minus 1 equals 0. That might make you panic, but just add your 1 to both sides, divide by that root 2. Good. You can leave it as 1 over root 2, or if it makes you happy to rationalize and go all the way to root 2 over 2. Now we ask ourselves, where do we have a cosine of root 2 over 2? Alea's right at 45. The bottom one, what's my 45-degree angle in the 4th quadrant? 315. Good. Good. All right, we got a little bit more time. We're gonna do basically these same problems, but the next set, do you see how it says solve 0 to 2 pi? What do I want my answers in this time? Radians. Radians, we want radians. Okay. I wanna do letter A now. Yeah, we can do letter A, okay. So if you notice on the last ones, we had 0 all by itself, so this time we need to move tangent over, so that tangent, so we have a 0 all by itself on the right side, so I'm gonna minus that tan from both sides. Tan x sine squared x minus tan x equals 0. So now we take that tangent out of everything, right? So we get tangent x, and then we get sine squared x minus 1 equals 0. And then just like we did before, we're gonna set each part equal to 0. Tan of 0, I think we just did a second ago. The only difference is I wanted in radians, not in degrees. So tan of 0 in radians would be and pi. 0 and pi. Now the sine one's a tiny bit funny, but I promise it's gonna work its way out in a second. When I do that one, I'll just kind of pop it over here a little bit, just so I have a little bit more space. So. Give me 1 second. Let's work our way there. One thing we have to do is add that 1 to both sides first. And then I have to square root that sine. So we're gonna square root. What is the square root of 1? 1, but it's also positive or negative 1. It could be a +1, it could be a -1. So we want to know every place that we have a sine of 1. So y is 1 at 90, which is what? Pi over 2 and good, 270. So we want both of those because it could be +1 or it could be negative. Awesome, let's jump to the next side. Let's do, if we have time, we'll do B and C. I'm not giving you homework tonight, and the more of these we can do right now, the more practice we have time for tomorrow, next class. I think it's online if you want to do it online. Guys, the notes are online, aren't they? Yeah. Yep, okay, perfect. Okay, so let's look at letter D, or letter B. On this one, I don't necessarily need to get that tan, squared, move everything to one side to equal 0, because I only have one trig function here. Could we just simplify this? How do I solve for tan to get that by itself? We're gonna square root both sides. So I get tan of x equals plus or minus square root of 3. And so now I'm ready to know what angle gives me a tangent of root 3, and I want all of the places where that happens. So I remember tan is y over x. And to get root 3, 60 could count. Let's see, 60 is 1/2 and root 3 over 2. And that would give me my y over my x. So yeah, that would give me my 60 degrees. And so I want my 60 degrees everywhere, and I want it in radians. What are my radians for 60? Good. What's another 60-degree radian? In the second quadrant would be 2 pi over 3. In the third quadrant, it would be good. And then what about in the last column? 5. All of my 60-degree angles. Because again, just like when we square root a minute ago, that square root makes us have to do the positive and the negative. And you guys are doing so great. Let's just do one more. On this one, do I need to move that sign to the other side? Yeah, I've got a lot of trig functions going on there. Let's move that sign over.
Why did you?
Notice how there's only one trig function over here? So I was able to, if I could just isolate tan X, I could solve for it. On all the other ones, I've got sine and tan, I've got sine and tan, I've got tan and cos, all that stuff. So we had to get everything to one side. When you just have one, you can leave it by itself. So sine X tan squared X minus sine X equals 0. Now what? Go take a sign out. Tan squared X minus 1. And then now we're gonna set each part equal to 0. So we'll do sine X equals 0. So I asked myself, where do we have a sine of 0? 0 and pi. And then we'll do our inside, we'll do our tangent squared X minus 1 is equal to 0. We'll add our 1 to both sides. We'll square root both sides. So we have tan of X equals plus or minus 1. What angle gives me a tan of plus or minus 1? 45. And so that's pi over 4, and we want all of our 45-degree angles. So pi over 4, what would it be in quadrant 2? 3 pi over 4. What would it be in quadrant 3? That's gonna be fourth quadrant. 5, good. Awesome. Oh, good work, guys. That was a lot. We have a tiny bit left of notes to do, and then we're gonna do more practice tomorrow on 5-1, so we can get this using our puzzle pieces. And then we've got a few days for basically everything else. Yeah, we're just moving and grooving.